So Facebook recently gave BYU a grant, and this is a very large project that I only worked on a part of it. But the grant was to help find a feasible plane design that can stay up in the upper atmosphere for long periods of time, the goal being a month to a year. Currently there is not a plane that can do that, and there are many people working on this problem. But my project was to help figure out how to optimize the whole system of the plane with its many subparts that have their own optimization routines. We initially tried this in two approaches. The first was a very basic and kind of just like a proof that it can be done concept called point-based iteration. Point-based iteration just means you optimize one subsystem, for instance, the battery of the plane, and then once it's best case for the current conditions, like the current flight path or the current propulsion mechanism, once the battery's the best, then you go on to the next one. You look just at the path optimization and hold the battery and propulsion mechanism constant. That's called point-based iteration. We just go sequentially through the subsystems. And that point-based iteration did not yield a feasible design, though it did make some improvements. And we're really looking to make this plane feasible, so we tried to implement something called MDO in this subfield. It's called Multidisciplinary Optimization. Multidisciplinary optimization is really hard because the question is, how can you optimize all the systems all together all at the same time? And that can be really hard because now you're increasing how many variables are changing by a lot. Now we have hundreds or thousands of variables depending on the problem. And a computer can really struggle to find the best design with so many different variables and so many options. It's like going to the bread aisle. Which bread do you choose? With thousands of options, the computer can struggle to find the best design. So what we tried to just take it to the next step is we tried coupling our subsystem optimizations. So we would do battery and path optimization together, and then path and propulsion, and then battery and propulsion, just to try to limit the size of the problem so that we could still coach the computer how to keep going towards optimal results. And as we did that, the optimizer actually found some unique and new results that haven't been well understood. And we didn't tell the computer to do these things. It decided that this was the best way to do it. One of those results actually is shown on this diagram. It's showing how the plane should fly its trajectory. So if you see that yellow vector up to this point, that's the direction of the sun. So if you're looking down on the plane, and this is how the flight path it's flying, this is where the sun is coming from at that current moment. And on this stretch of the flight path, the optimizer told the plane you need to fly essentially as fast as possible, as fast as would be normally used by those motors. Try to get through that and fly straight. Just get through that phase so that as it's coming around, it tells the plane bank back, lean back so that the solar panels on the wings can get as much sun as possible on that stretch of the trajectory. As well, it has an additional benefit. As it banks back, it slows the plane down, making it so that the battery can charge more because it has more time to get as much sun as possible as it's leaning back. So that was a very unique result that the optimizer found. It also found something else is super new and unthought of, or not thought of, is that because the battery optimizer decided it found an optimal battery weight, that if you made the battery any bigger to potentially hold more energy, it actually made the plane worse because so much weight would make it harder to fly. So with that optimal battery, the optimizer decided, well, once the battery's full, start flying up. Start going up and gain in altitude, thus gaining more potential energy rather than electrical energy because the battery's full. And then once you hit nighttime and there's no more sun, the plane can now just coast down and use very little energy, very little battery energy, and just coast down and use all of the potential energy to get back to where it was before. And in that coast down, especially as the sun is going down, the optimizer found that it was best to make a funnel type shape. So a big circle, and as it's going down, get smaller and smaller circles, as is shown in this graph. And the reason we think that is more optimal is because as it's going down, it's trying to make more loops to get the last drops of sunlight, you could say, because the sun's going down. And those smaller loops are more efficient and gain more energy. And as the sun's going down, it's trying to get as much energy as possible. Yeah, so those were the main findings of our optimization technique. Currently, these findings still don't make a feasible aircraft design, but we're currently working on trying to have a better airfoil design for the aircraft, and we have very good indication that will make a feasible aircraft design, though we still need to explore it just as everybody else is trying to explore this problem. Thank you so much.